And that assumption explains why the steps are what they are. I've got to figure out lambda, and I've got to figure out a corresponding set of k's. I like it.
So the x prime is your dx dt, dy
Yes,
dt.
because x is xy, x prime is dx dt, dy dt.
Oh, yeah,
I love it.
makes sense.
And the a is just the collection of constants. I like it. That was a beautiful idea in the first place, to be honest. I mean, the math is the same, but it's just the way to attack it is so much quicker. So here, what do you get here? You just get, you'll notice you'll just get diagonals with negative lambda, right? So 4 minus lambda, negative 7, 5, negative lambda. Do you guys understand that if I would have made it lambda minus 4 and lambda, it's the same result? Do you guys see that? But again, like I said, just so it matches with the book. And this is actually the way it's normally done. I have no idea why, to be honest. Equals 0. Then you get your characteristic equation. And from that, you can get your eigenvalues. And from that, you can get each set of eigenvectors. So again, I know I've said this before, but it's always good. The solution is found once I know lambda and I know the corresponding case. So here, when I multiply this through, I just get lambda squared minus 4 lambda plus 35. Oh, I would do one that's like this, wouldn't I? That won't factor, will it?
No.
No. So, what do you have to do?
Or drive a function.
Ah, yeah.
Using lambdas.
Yeah.
Oh.
Who cares? Lambda is just a variable.
X.
You need to do this.
Yeah, yeah. 4 plus or minus square root 16 minus 140. Oh, it's complex
Yeah.
even. I love it. 16 minus 140, so negative
This is a plug problem.
124 over 2, 31, so 2 rad 31, 2i rad 31. So 2 plus or minus I, is that true? I think. Yeah. All right, now watch. This is grosser than I wanted, but too bad. So lambda 1 is 2 plus I rad 31, and lambda 2 is 2 minus I rad 31. You guys are excited about this. So now I look back at this, and I throw this stuff in. So I get, you ready? For this one I get 4 minus 2 minus I rad 31, negative 7. 5, where'd it go? Negative 2 minus I rad 31 times k, 1k2 equals 0. I don't know why I did 4 minus 2. I love that. So this is just 2 here. Is that cool?
Yeah.
Plus,
So again?
plus the other one. Because lambda is negative. The second one.
Yeah, so this will be 4 and then minus this whole thing.
Okay.
And then negative this whole thing. I haven't done that one yet.
Oh, okay.
Yeah, that's a separate thing. Yeah. So for lambda 1, I've got to investigate its k. And then for lambda 2, I do it again. Yeah. So let's see. We get 2 minus I rad 31 k1 minus 7 k2. And 5 k1 minus, let's say this, minus 2 plus I rad 31, like that, k2. Yes.
What happened right there underneath the a minus lambda I times k equals 0? What's that next?
So this is what a minus lambda I looks like for this
So you find a
option. So really, it's right here, right? 4 minus that, bam. And then negative that, bam. I've got the form right here, right before I get my characteristic equation. That's beautiful. That is not beautiful, but I think I know what's going to happen here, and I have a unbelievable knack for choosing a problem that's early in the homework set, but that's really gross.
Where'd that squared term come from?
This here?
Yeah.
That's just what 4 minus 2 is. I just didn't want to rewrite the whole thing.
Alright.
That's my bad. Let's see if my guess is right, and if it isn't right, I'm just going to try to find what's a little bit better. We're just trying to get the feel for this, Jeff. My God.
Well, since it's a complex number, it must be in the form of
You ready?
cosine and stuff like that, right?
Look at the first one. If I solve for K1, I get 7 over that, right? If I solve for K1 and the other one, I get, I would add that stuff over, so I get 2 plus I rad 31 over 5. Now my bet is that if I rationalize this, or multiply by the complex conjugate, let's see what happens. Just for shits and giggles, let's see what happens. So if I multiply, does this feel familiar at all, what I'm doing right now?
2 plus 5.
Right, so that would lead to K1. I'm hoping it comes out to this. Let's see what it does. So it's 7 times 2 plus, I'm not going to do that yet because that's what's supposed to happen up there. And this is 4. Oh no, this is not going to come out the way. Will it? Yeah. Yes, it will. Oh, this kicks so much ass. Have faith, Jeff. 4 minus I squared, which is plus 1, so 4 plus 31. Which is 35, so that reduces to 2 plus I rad 31 over flippin' 5, the same answer, right? Not immediately obvious that they're the same answer. The earlier ones were obvious. 3x plus 3y, 2x plus 2y. It's like, oh yeah, they got the same answer. This one, not so obvious. Let me stop here for a second. Oh, and I lost by, how did I lose this poor little K2? Yeah, I lost my poor little K2, right? Poor little K2. Just lost him. Okay. So whatever K2 is, K1 is that times it. So I know this K is going to be whatever K2 is. K1 is going to be 2 plus I rad 3 over 5 K2. What type of answers do you think a complex solution like this would lead to? Same ones that it would lead to before.
Cosine sine?
Cosine and sine. I like it. So let me do this with the time. We could do the other lambda. It would be very, very similar to what we just did. Let me take a step back and find a problem that isn't so desperately evil.
What's K2s in that 2 plus root 5?
Oh, I see why that's evil. Because I took it out of section A1. Smart. The section where you don't have to solve anything. Here, let's do this. All right. So here we go. Let's try another one. This definitely got a much nicer answer. To be honest, I did not assign anything that dealt with this, because this is that complex case that I didn't want to get into that I just accidentally got into. I'm sorry. Okay, let's try another one that's a little bit nicer to look at so you guys can see the process a little bit better instead of getting lost in the complex weeds. So like this one, let's see, let's just be really safe, Jeff, and take number 1. I like it. that sucks, man. Getting old sucks. I'm gonna have to start wearing my reading glasses just to look at the book. All right, let's do this one together. Considering I just took you through a little math horror house here. So this would be x prime equals something x, and that something, of course, is
1 minus lambda. Or just
1, 2, 4,
1,
3.
2, 4, 3. So then you can identify what a is, and then I can jump, based on what we did earlier, I can jump to that part that's the most important. So I can look at what a minus lambda is. So what is a minus lambda I? Here's going to just be, like Stephen starts saying, 1 minus lambda, 2, 4, 3 minus lambda. You guys, I mean, that's, I love that shit. Equals 0. And the thing to remind yourself about, two things. One, you got to remind yourself why this works. You got to go back to how we derived up to this step and why we can just jump to this step. We know it's gonna lead us there. Secondly, we're only covering this for one day, so I'm not going to give you something remarkably heinous on the test. You with me? That doesn't mean don't worry about it at all. It just means I'm not going to give you like this. So what do I get here? I get, can I just, lambda squared minus 4 lambda plus 3 minus 8. So I get lambda squared minus 4 lambda minus 5. Thank God that's factorable. So I get lambda minus 5, lambda plus 1 equals 0. So I get my 2, I get lambda equals 5, and lambda equals negative 1. Let me see. You guys try to take the next step for lambda equals 5. See if you can set up the next step. So for lambda equals 5, this just looks like negative 4, 2, 4, negative 2. So then you end up with, so you get negative 4k1 plus 2k2 equals 0. The other one's the same equation, right? Just both by both sides, but it's negative. When it's complex, it's not as immediately obvious, as we saw, that they're the same. Here I get, I don't know why I just always solve for k1, but here, all right, let's solve for k2 now. Here I get k2 is, add that over, divide by 2,
2K1.
2k1. Oh, just to be different. It does not really matter. This is equivalent to taking a DE a system of DEs, solving for y first and get a relationship with the c's, or solving for x first and get a relationship with c's. If you've ever seen it, both they're like inverse. If one was 2c1 and c1, then the other way would be c1 and 1/2 c1. It just captures that relationship. One is twice the other one.
So, yeah, I was going to ask that regarding 4, 9. I was just like,
Yes.
So as long as you showed that they were both different, then that would be right in like the test scenario? Wouldn't
Yeah, as long as you capture that relationship, as
Okay.
long as you make the constants equivalent, showing up in both, but then you got whatever
I was banging my head.
coefficient. Yeah, don't bang your
I was
head
doing the homework.
unless it's
It sounds like it's not the same.
part of your Friday night. But so now I've got that. So now I know that this little dude looks like whatever K1 is, K2 is twice that. So it looks like 1, 2, just to really put it down without the constants. For lambda equals -1, same idea. Right? What's it look like for that guy? It's going to be 2, 2, 4, 4. Yeah, so you get whatever k, so if I solve for k2 again, k2 has got to be equal to -k1 for that to be true. I like it. And of course, this is like the zero matrix if you want to get all. So this will be whatever k1 is, k2 is negative that, so this will be 1, -1. So lambda equals 5 relates to e to the 5t. Lambda equals -1 relates to e to the -t. So here's the idea. The solution matrix looks like, without the constants in there, 1, 2 times its lambda solution. Right, those go together. That k goes with its lambda. Plus 1, -1 times its lambda solution. I'm going to give you a clean one that I wasn't trying to compare to an answer we got earlier. That's the nice way you can kind of just put them together. So those k's go with their lambda solution piece. Right? This is all one big thing. And of course those k's go with their lambda solution piece. So then what's x of t? E to the 5t plus e to the -t. And I can throw constants in there, right? And what's y of t? 2e to the 5t minus e to the -t. I like it. And you can throw constants in there, that's fine. Yes?
If you solve for the other k, it should still work, right?
Yeah, of course. Because if this is a 2, that would be, if that becomes a 1, that's got to become a 1/2. To maintain the relationship between the two. The relationship between the two is what's important. That's why in 4.9 you had to have C1 and C1 so you can see the relationship. If one's C1 and the other one's C3, I can't see the relationship between the two. Okay, I like it. And again, if you guys start to realize, why do I not really put constants down here all the time? You can just throw them in now, because now the idea is this is sort of a basis set of things, and I can do any linear combination of these things to get other solutions to this DE system. We're not going to go too deep that way. Don't worry about it. So if you don't put constants down, I'm fine, because that's basically like the place to get to. Because now you can throw constants in there as you want to do linear combinations of those. I don't know how much the book gets into that. Yeah, they throw constants in there at the end. I like it. Blah, blah, blah. Yeah, so I only did 3 through 12. I still have to put them up on the web assignment, so somebody remind me. So for section A2, it's only 3 through 12. It's just the real, unrepeated lambdas. You can imagine there's cases just like there were before that you have to interpret. So this would be a case to become cosine sine, just like before. I didn't take this there. I figured this would be enough for now. So remind me about the web assign, and you already reminded me about the practice test, right? Okay.
So the homework is just A1 or
A2.
Oh,
Yeah. 8.1 is just the preliminary write this in matrix form and some terminology that you might need to read about. But
So we're not doing any of the complex stuff on the test or not?